Welcome to our comprehensive exploration of alcohols, phenols, and ethers in organic chemistry. These compounds play a crucial role in both academic studies and real-world applications, from pharmaceuticals to industrial solvents. In this video, we'll break down their structures, properties, and reactions, making complex concepts easy to understand. Whether you're a student preparing for exams or simply curious about organic chemistry, this journey will help you grasp the essential. Let's start by understanding what makes alcohols, phenols, and ethers unique, and why they are so important in the world of chemistry. Alcohols are organic compounds characterized by the presence of one or more hydroxyl OH groups attached to a saturated carbon atom. The general formula for a simple alcohol is ROH, where R represents an alkyl group. Alcohols are classified based on the number of carbon atoms bonded to the carbon bearing the hydroxyl group, primary, secondary, or tertiary. This classification affects their chemical reactivity and physical properties. Alcohols are widely found in nature and are essential in various industries, including medicine, cosmetics, and fuel production. Alcohols can be classified into three main types: primary, secondary, and tertiary. In primary alcohols, the carbon atom attached to the O group is connected to only one other carbon atom. In secondary alcohols, it is attached to two other carbons, and in tertiary alcohols to three. This classification is important because it influences the alcohol's reactivity, especially in oxidation and substitution reaction. Understanding these differences helps chemists predict how each type of alcohol will behave in various chemical processes. Alcohols exhibit unique physical properties due to the presence of the hydroxyl group. They are generally polar molecules, which allows them to form hydrogen bonds with water and other alcohol molecules. This results in higher boiling points compared to similar-sized hydrocarbons. Alcohols are often soluble in water, especially those with shorter carbon chains. As the carbon chain length increases, solubility decreases. These properties make alcohols versatile in both laboratory and industrial settings. Chemical properties of alcohols are largely influenced by the hydroxyl group. Alcohols can undergo oxidation, dehydration, substitution, and esterification reactions. For example, primary alcohols can be oxidized to aldehydes and then to carboxylic acids, while secondary alcohols oxidize to ketones. Tertiary alcohols are resistant to oxidation. Dehydration of alcohols leads to the formation of alkene. These reactions are fundamental in organic synthesis and industrial processes. Alcohols can be prepared through several methods, including hydration of alkenes, reduction of carbonyl compounds, and fermentation of sugars. Hydration of alkenes involves adding water across a double bond, while reduction of aldehydes and ketones uses reducing agents like NABH4 or LiAlH4. Fermentation is a biological process where sugars are converted to ethanol and carbon dioxide by yeast. Each method has its own significance in laboratory and industrial applications. Alcohols have a wide range of uses in everyday life and industry. Ethanol, the most common alcohol, is used as a solvent, fuel, and in alcoholic beverages. Methanol is used as an industrial solvent and antifreeze, but is toxic to humans. Isopropanol is commonly used as a disinfectant and cleaning agent. The versatility of alcohol stems from their ability to dissolve both polar and nonpolar substances, making them valuable in various chemical processes. Phenols are a special class of organic compounds where a hydroxyl group is directly attached to an aromatic benzene ring. This structure gives phenols unique chemical properties compared to alcohols. Phenols are known for their antiseptic properties and are used in the production of plastics, drugs, and dyes. The presence of the aromatic ring makes phenols more acidic than alcohols, influencing their reactivity and application. The defining feature of phenols is the direct attachment of a hydroxyl group to a benzene ring. This arrangement allows for resonance stabilization, which increases the acidity of phenols compared to alcohols. The aromatic ring also affects the types of reactions phenols can undergo, such as electrophilic substitution. Understanding the structure of phenols is essential for predicting their behavior in chemical reactions and their role in various industries. Phenols are typically solid at room temperature and have higher melting and boiling points than similar alcohols due to strong hydrogen bonding. They are moderately soluble in water, but their solubility decreases with increasing size of the aromatic ring. Phenols often have a distinct odor and can be irritating to the skin. These physical properties are important for their handling and use in laboratory and industrial settings. Phenols are more acidic than alcohols due to the resonance stabilization of their conjugate base. They react with bases to form phenoxide ions and can undergo electrophilic aromatic substitution reactions, such as nitration and halogenation. Phenols are also prone to oxidation, forming quinones. These chemical properties make phenols valuable in the synthesis of pharmaceuticals, dyes, and polymers. Phenols can be prepared through several methods, including the hydrolysis of chlorobenzene, the oxidation of benzene derivatives, and the decarboxylation of salicylic acid. The most common industrial method is the cumene process, where cumene is oxidized to cumene hydroperoxide and then acidified to yield phenol. Each preparation method has its own advantages and is chosen based on the desired scale and purity. Phenols are widely used in the production of plastics, such as Bakelite, and in the synthesis of drugs like aspirin. They also serve as antiseptics and disinfectants due to their ability to denature proteins. In addition, phenols are important intermediates in the manufacture of dyes, resins, and explosives. Their unique chemical properties make them indispensable in various industries. Ethers are organic compounds characterized by an oxygen atom connected to two alkyl or aryl groups. Their general formula is ROR. Ethers are relatively unreactive compared to alcohols and phenols, making them excellent solvents for many organic reactions. They are commonly used in laboratories and industries for their stability and low reactivity. Structure of ethers consists of an oxygen atom bonded to two carbon-containing groups, which can be either alkyl or aryl. This arrangement gives ethers their characteristic properties, such as low boiling points and limited hydrogen bonding compared to alcohols. The oxygen atom in ethers is sp3 hybridized, resulting in a bent molecular shape. Understanding the structure of ethers is essential for predicting their behavior in chemical reaction. Ethers are generally colorless, volatile liquids with pleasant odors. They have lower boiling points than alcohols of similar molecular weight due to the absence of hydrogen bonding between ether molecules. Ethers are slightly soluble in water, but are excellent solvents for many organic compounds. Their volatility and flammability require careful handling in laboratory and industrial environments. Ethers are relatively inert and do not react easily with acids or bases. However, they can undergo cleavage reactions with strong acids, such as HI or HBr, resulting in the formation of alcohols and alkyl halides. Ethers are also susceptible to oxidation, forming peroxides, which can be hazardous. Their chemical stability makes them useful as solvents in many organic reactions. Ethers can be prepared by several methods, the most common being the Williamson ether synthesis. This involves the reaction of an alkoxide ion with a primary alkyl halide. Another method is the acid-catalyzed dehydration of alcohols, which is mainly used for the preparation of symmetrical ethers. Each method has its own advantages and is chosen based on the desired ether and reaction conditions. Ethers are widely used as solvents in laboratories and industries due to their chemical stability and ability to dissolve a wide range of substances. Diethyl ether was historically used as an anesthetic, though safer alternatives are now preferred. Ethers are also used in the production of pharmaceuticals, perfumes, and as starting materials for chemical synthesis. Alcohols, phenols, and ethers each have distinct structures and properties. Alcohols contain a hydroxyl group attached to a saturated carbon, phenols have a hydroxyl group on an aromatic ring, and ethers feature an oxygen atom between two carbon groups. These differences influence their physical and chemical behaviors, including acidity, solubility, and reactivity. Understanding these distinctions is key to mastering organic chemistry. Phenols are significantly more acidic than alcohols due to the resonance stabilization of the phenoxide ion formed after losing a proton. Alcohols, lacking this resonance, are much weaker acids. This difference is important in chemical reactions and influences how these compounds interact with bases and other reagents. Recognizing the acidity trend helps in predicting reaction outcomes. Both alcohols and phenols can form hydrogen bonds due to the presence of the hydroxyl group. This ability leads to higher boiling points and greater solubility in water compared to ethers, which cannot form hydrogen bonds as effectively. Hydrogen bonding also affects the physical properties and interactions of these compounds in biological and chemical systems. Reactivity of alcohols, phenols, and ethers varies based on their structures. Alcohols are reactive towards oxidation and dehydration, phenols undergo electrophilic substitution, and ethers are generally inert but can be cleaved by strong acids. Understanding these trends is essential for predicting the outcomes of organic reactions and designing synthetic pathways. Alcohols can be oxidized to form different products depending on their classification. Primary alcohols oxidize to aldehydes and then to carboxylic acids, secondary alcohols to ketones, and tertiary alcohols are resistant to oxidation. These reactions are fundamental in organic chemistry and are widely used in laboratory and industrial processes. Alcohols can undergo dehydration reactions in the presence of acid catalysts such as concentrated sulfuric acid to form alkenes. This reaction involves the removal of a water molecule and is an important method for producing alkenes in the laboratory. The ease of dehydration depends on the structure of the alcohol, with tertiary alcohols dehydrating most readily. Alcohols can participate in substitution reactions, where the hydroxyl group is replaced by another group, such as a halide. These reactions often require acid catalysts or reagents like thionyl chloride or phosphorus tribromide. Substitution reactions are important for converting alcohols into other functional groups in organic synthesis. Alcohols react with carboxylic acids in the presence of acid catalysts to form esters and water. This process, known as esterification, is widely used in the production of fragrances, flavors, and plastics. The reaction is reversible and can be driven to completion by removing water from the reaction mixture. Phenols readily undergo electrophilic aromatic substitution reactions due to the activating effect of the hydroxyl group. Common reactions include nitration, halogenation, and sulfonation. These reactions are important for synthesizing dyes, pharmaceuticals, and other aromatic compounds. The position of substitution is often ortho or para to the hydroxyl group. Phenols can be oxidized to form quinones, which are important intermediates in the synthesis of dyes and pharmaceuticals. The oxidation process involves the loss of hydrogen atoms from the hydroxyl group and the aromatic ring. Quinones have distinctive colors and are used in various chemical and biological applications. Ethers are generally stable, but they can be cleaved by strong acids such as hydriodic acid HI or hydrobromic acid HBr. This reaction results in the formation of alcohols and alkyl halides. The cleavage of ethers is important in organic synthesis and must be carefully controlled due to the potential formation of hazardous byproducts. Ethers can react with oxygen from the air to form peroxides, which are highly explosive and dangerous. This process is slow but can occur over time, especially in diethyl ether. Proper storage and handling of ethers are essential to prevent peroxide buildup and ensure laboratory safety. Alcohols are vital in numerous industries, from fuel production to pharmaceuticals. Ethanol is used as a biofuel and solvent, while methanol serves as a feedstock for chemicals and plastics. The versatility and reactivity of alcohols make them indispensable in manufacturing, healthcare, and research. Production and use of alcohols have environmental implications. Ethanol as a biofuel can reduce greenhouse gas emissions, but large-scale production may impact food supply and land use. Methanol and other alcohols can be toxic if released into the environment. Responsible production and disposal are essential for minimizing negative impacts. Phenols are present in many products we use daily, from disinfectants to plastics. Their antiseptic properties make them valuable in healthcare, while their role in polymer production is crucial for manufacturing durable materials. Understanding the presence and function of phenols helps us appreciate their importance in modern life. Ethers have played a significant role in medicine, especially as anesthetics. Diethyl ether was one of the first anesthetics used in surgery, revolutionizing medical procedures. Although safer alternatives are now available, ethers continue to be important as solvents and intermediates in pharmaceutical synthesis. Handling alcohols requires proper safety measures due to their flammability and potential toxicity. Always use alcohols in well-ventilated areas, avoid open flames, and wear appropriate protective equipment. Understanding the risks and following safety protocols ensures safe laboratory and industrial practices. Phenols can be corrosive and toxic, requiring careful handling. Always wear gloves and eye protection when working with phenols and avoid skin contact. Proper storage and disposal are essential to prevent environmental contamination and health hazards. Ethers are highly flammable and can form explosive peroxides. Store ethers in tightly sealed containers away from heat and light and regularly test for peroxide formation. Use ethers in well-ventilated areas and follow all laboratory safety guidelines to prevent accidents. Alcohols are found in many biological systems, playing roles in metabolism and cellular processes. Ethanol is produced by yeast during fermentation, while other alcohols serve as intermediates in biochemical pathways. Understanding the function of alcohols in biology helps explain their effects on living organisms. Phenols are naturally occurring compounds found in plants where they contribute to flavor, color, and defense mechanisms. Many antioxidants in fruits and vegetables are phenolic compounds which help protect cells from damage. The study of natural phenols is important in nutrition and medicine. Ethers are essential in various industries, including pharmaceuticals, perfumes, and chemical manufacturing. Their ability to dissolve a wide range of substances and their chemical stability make them valuable as solvents and intermediates. Ethers are also used in the production of fuels and lubricants. Alcohols are present in many household products, from hand sanitizers to cleaning agents and cosmetics. Their ability to dissolve oils and kill bacteria makes them effective in hygiene and personal care. Recognizing the presence of alcohols in daily life highlights their practical importance. Phenols have significant medicinal uses, including as antiseptics and in the synthesis of drugs like aspirin. Their ability to denature proteins and disrupt cell membranes makes them effective against bacteria and fungi. The development of phenol-based drugs continues to be an important area of pharmaceutical research. Ethers are used in the development of new materials and technologies, including as solvents in electronics manufacturing and as components in fuel cells. Their chemical stability and low reactivity make them ideal for specialized industrial applications. The ongoing research into ethers is expanding their role in modern technology. This video, we've explored the fascinating world of alcohols, phenols, and ethers. We've covered their structures, properties, preparation methods, and uses in various fields. Understanding these compounds is essential for mastering organic chemistry and appreciating their impact on everyday life and industry. Keep exploring and applying these concepts as you continue your journey in chemistry.